Standard feed-forward neural networks have a strict architectural constraint. You feed them a fixed-size input array, and they map it to a fixed-size output array. Each input is processed entirely independent of the last. If you hand the network a series of data points, it has no structural concept of before or after. It is entirely blind to time. But most real-world data is sequential. For text arrays, audio frames, or stock market prices, meaning is dictated by the exact order of the inputs. To process this data, we use a recurrent neural network. This architecture introduces a hidden state vector. Think of it as an internal, dynamic memory that gets continuously updated and passed forward from one time step to the next. We are going to build an RNN from first principles. We will trace its exact mathematical operations, and by doing so, prove structurally why it inevitably collapses when processing long sequences. Diagnosing these exact mathematical failure states is a mandatory prerequisite for understanding the architecture that replaced it, the transformer. To feed discrete categorical data, like text characters, into the network, we must first convert them into numbers. Each character is assigned an integer, and then encoded as a sparse one-hot vector, an array of zeros with a single 1. At any given time step, the RNN cell receives two distinct inputs. It takes the current one-hot vector, known as xt, and the memory vector from the previous step. The cell combines inputs using two weight matrices. The input matrix, wxh, projects the character into a hidden dimension. Simultaneously, the recurrent matrix, whh, transforms the previous memory. The two resulting equal-sized arrays are then summed together. We pass this sum through a hyperbolic tangent activation function, or tan, squashing every value between -1 and +1. Without this non-linear compression, compounding matrix multiplications will cause the entire system to collapse into a single linear transformation. The matrices inside this cell are not unique to this step. The network uses weight sharing. The exact same wxh and whh matrices are applied recursively at every single time step. Reusing the same parameters at every step allows the network to process variable length sequences. But this recursive structure means every calculation at step 50 is inextricably linked to step 1. To understand the impact of that linkage, we need to look at the macro architecture used for machine translation. This sequence-to-sequence design connects two distinct RNNs together, an encoder and a decoder. The encoder reads the source sequence step by step, compressing its entire semantic context into a final hidden state vector. This creates a severe bottleneck. Whether 3 words or 3,000, all data must be mathematically compressed into that exact same fixed dimension array. The decoder takes this isolated bottleneck vector and begins generating the translated sequence autoregressively. It predicts one word and then feeds that prediction back into itself as input for the next step. During training, we use teacher forcing, feeding the correct target words into the decoder to stabilize learning. But during inference in the real world, the decoder is entirely on its own, relying solely on its own previous predictions. Because of this autoregressive design, one mathematically poor prediction at step 3 permanently corrupts the input for step 4. There is no mechanism to correct early mistakes. The errors cascade. Forcing high-resolution sequential data into a rigid, fixed-length spatial vector guarantees that the context from the beginning of a long sequence is irreversibly degraded by the time the decoding process even begins. To train this network, we have to optimize those shared weight matrices. We do this by calculating the gradient using the chain rule. But recurrent networks introduce a mathematical complication. The hidden state at step 50 relies on step 49. The chain rule cannot just move straight down through layers. It must be pushed backward through sequence time. This is backpropagation through time.
We begin with the output gradient, computing the initial derivative of the cross-entropy loss with respect to the raw logits. To pass this gradient backward to the previous step, we execute a specific mathematical operation. At every single step, the gradient is multiplied by the transpose of the recurrent weight matrix. The second half of that backward step requires multiplying by the derivative of the tan-h activation function. The maximum value of this derivative is exactly 1. Because the weight matrices are shared, The network must accumulate these gradient contributions across all 50 time steps before making a single parameter update. This reveals a fatal algebraic consequence for the network. Chaining derivatives backward means we are continuously multiplying the exact same numbers together, step after step. This continuous compounding multiplication makes the gradient flow highly unstable. The parameter updates cease to be a linear adjustment and instead transform into an exponential function of the sequence length. If the largest eigenvalue of the recurrent weight matrix is strictly greater than 1, that continuous multiplication causes the gradients to grow exponentially. This is the exploding gradient problem. When the gradient explodes, the network makes wild, chaotic updates to its weights. The loss spikes into errors, resulting in total training collapse. The standard engineering fix is a brute force mechanism called gradient clipping. We artificially cap the maximum magnitude of the gradient to prevent it from reaching critical mass. This chart plots the opposite, more insidious threat, the vanishing gradient. If weights evaluate to less than 1, the continuous multiplication causes the gradient to shrink exponentially as it moves backward. When the gradient vanishes, the network mathematically loses its ability to update weights based on data from the beginning of the sequence. The model develops acute short-term memory. To mitigate this, engineers use Xavier initialization, carefully scaling the starting weights by 1 over the square root of the input size. This prevents the initial forward pass from immediately pushing values into the extremes of the tanh function, where the derivative drops to 0. Another tactic is replacing the tanh activation entirely with a leaky ReLU function. This ensures the derivative remains a constant positive value. Finally, we apply batch normalization. This acts as a manual reset for the mean and variance of the data flowing between layers. These 3 techniques, initialization, activations, and batch normalization, are now foundational building blocks used across all deep neural networks. But they are stopgaps. They prevent immediate mathematical failure, but over sufficiently long sequences, the vanilla RNN architecture simply cannot survive the exponential decay mandated by backpropagation through time. The recurrent neural network is constrained by 2 irreconcilable architectural flaws: the fixed-length information bottleneck of the encoder and the recursive gradient decay of backpropagation through time. Because of these structural realities, recurrent architectures excel at immediate temporal processing. They predict the very next word flawlessly, but they systematically fail at capturing long-range dependencies. This led researchers to a specific engineering question: how do we bypass the chain entirely? How do we prevent early sequence context from being mathematically diluted by later time steps? The conceptual solution is to abandon the single compressed historical vector. Instead, the decoder must be granted selective access to the entire sequence history simultaneously. This mechanism is known as attention. It allows the network to dynamically assign weight directly to any source state, entirely bypassing the temporal distance between them. The mathematical constraints of RNN memory defined the search for a more robust architecture. Solving the gradient and bottleneck problems led to attention, the structural foundation of the modern transformer.